The third question was about the compression ratio of an Otto cycle and a diesel cycle. Okay, so let's take up that. Detailed analysis of the cycles I will just describe in a few minutes, but I will not go into the detailed arithmetic of it. It is there in everywhere on the books on the web. You can see the full detailed derivation. What I have done here is just displayed the final formula. And now let's be clear. What is it that we are talking here about? We are looking at what I started discussing yesterday as air standard cycles. We did not have, firstly, they are all reversible. And we said yesterday that the working substance behaves like an ideal gas. We made a differentiation between what happens at the exhaust versus the cooling process. The cooling process is replaced by exhaust and by the intake. So air standard cycles are, it's a closed cycle, unlike the closed system that we have looked at, and real cycles are open systems. Because after the combustion is done, and of course the heating is replaced by a combustion process. So those are all the major differences between real cycle and air standard cycle. Three major differences, and you should keep that in mind. And the reason we convert this real cycle into an air standard cycle is because it gives us a very quick and easy way to do the analysis and come up with some very quick ballpark numbers. But remember, this is an idealization, and the real cycles will be quite different and definitely less efficient than what these numbers tell us. In a course like this, we don't go into analysis of real cycles. We will just look at the first order analysis of these practical cycles. So these are the formulae. Thermal efficiency of Otto cycle is 1 minus 1 over R to the power K minus 1, where R is called the compression ratio. So what is compression ratio? We just take in this cycle is that we have a cylinder piston arrangement where the piston moves between this extreme position and this extreme position. And this is a standard machines, whether it's a compressor or whether it is a reciprocating internal combustion engine. So this is called the top dead center. And this is called the bottom dead center. And this much volume got compressed to this. So the ratio of this is called the compression ratio. So we can say this is volume at the bottom dead center divided by volume at the top dead center. It tells you how much you compress that gas. And if you look at the complete analysis of this cycle, the air standard Otto cycle will look like this. I am plotting V here and pressure here, and we say when the piston goes up and down, how does pressure vary, and what is heat transfer in each process, what is work transfer in each process. This is what we want to know. So what happens here is, in the compression process, we start from say here and we reach a point over there. This will be a solid line because I'm showing that these are ideal process, but right now I'm just showing this. This is state 1, this is state 2. Then the ideal cycle, we have constant volume heating. So from here it goes and gets to state 3. This is constant volume heat addition. And after that, the piston has to come back to its original position, so it expands from here and comes back to this state, which is 4. And from 4 to 1, this is, so this was 1, 2 to 3, and 4 to 1 is again a constant volume Q out, cooling process. So this cycle and whatever is the substance inside this, and in all these cycles we assume that that substance is an ideal gas. So PV equal to RT is the equation of state. This can be applied. This is isentropic process. This is an isentropic process. And we can start doing the complete analysis from everything that we have learned. Process by process, we write the equations and we say this is from process 2 to 3. This is a closed system. We write Q23 is W23, which is 0, plus U3 minus U2, which is CV0 T3 minus T2. So similarly, every process can be written in terms of Cp, CV0 and the temperatures. And then the net work output, we can calculate that there was no work here, there is no work here. So the work output, net work output is W3 to 4 minus W1 to 2. And the heat input to the system was happening between Q2, 3, and this is the net work of the cycle. So the ratio of this net work, Wn, divided by Q2, 3, this is the thermodynamic efficiency of the air standard Otto cycle. And when you solve all these things by putting all these T's and CP's and CV's, we get the relation which is the first equation here, this one. 1 minus 1 upon R, K to the power, R to the power K minus 1. So this is the exponent. When you keep increasing R, gradually the efficiency goes up. As R gets higher and higher, the thermal efficiency doesn't increase that much. The benefit of pressure is getting lost. The second part was what happens in a diesel cycle. And here the story is slightly different. But the heat addition now is at constant pressure. So it goes there, and this is heat addition at constant pressure Q3. After that, we have exactly the same story. Expansion, which is isentropic, this was isentropic, and then a constant volume cooling. So these two processes and the cooling process are the same features as the Otto cycle, but this, which is the diesel cycle, the heat input is at constant pressure. So one cycle was heat, this is heat transfer constant pressure. The earlier cycle was heat transfer at constant volume. The Carnot cycle required it to be at constant temperature. That we argued yesterday is not possible. Point or this point or that point. That's a choice we have to make in addition to this and this distance. So first is the compression ratio, R, which was again V1 divided by V2, or you can take V4 by V2, doesn't matter. The second, cutoff ratio, that is This is defined as V3 upon V2. And when you do all the, again the same concept applies, we look at each fluid. This is a closed system, and ideal gas is the working substance again. And when you do all of that, we get a formula which is like the second one here. Thermal efficiency is 1 minus 1 upon R to the power K minus 1. So this part is same as the Otto cycle, but now we have part sitting there where RC, which was the cutoff ratio, that has come in. So depends on what RC one takes and begins to compare these two. But in general, if you just take these two and see which have got efficiency, it will turn out that the Otto cycle efficiency is slightly greater than the diesel cycle efficiency. But there is a little problem here. Otto cycles use which is in the range of 7 to 9 or 7 to 10, not more than that. And that's because what in this cycle, in the real cycle, is that we have an intake stroke which starts from here and it takes in the substance, and what it intakes is air plus vaporized fuel, a fuel vapor mixture. And then it is compressed to this point where the temperature is T2. And this T2 is less than the auto ignition temperature of this mixture. Otherwise, it can explode by itself and the rest thing can happen. And for that reason, the pressure ratio here is kept 7, 8, 9 in that type of range. In diesel cycles, what we have drawn here, the intake stroke is there when it takes in only air. So there is no danger that you can compress it as much as you want. There will be no explosion or no ignition. So compression ratios here could be anything from 14, 18, 20, even 22. So the temperatures here, T2, in the diesel cycle will be much larger than the temperatures at the end of the compression process in the Otto cycle. So that gives an advantage to diesel cycles, that because of this higher temperature at which then heat input takes place, overall the average temperature at which TH takes place is greater for diesel cycle than for Otto cycle. And that's why diesel engines in general have higher efficiency than Otto cycles. To complete the real life treatment, air standard cycle is what we do here. The real cycle gets an additional thing. It takes in air, then compresses it, goes through it, and then it goes back over there and comes back to this state. So this we can call it zero state. Intake, outlet, there are two strokes. Then there is one stroke for compression and one is for power stroke. So each stroke is 180-degree rotation of the crankshaft. And so to take 4 strokes, you need 2 revolutions. There were 2-stroke petrol engines. I won't go into the details of it, what the problems are. There also you do the same thing. You got 2 more strokes sitting over there. But those are now pretty much on the way out because of the pollution effect and the lower thermal efficiency. But 2-stroke diesels are very much alive in big numbers, and all the big engines are all diesels. The next thing you should remember is that it is the same engine which, instead of burning fuel as a petrol vapor, is also used with natural gas. And this ignition here happens by putting a spark into it, which will cause it to explode. So a gas engine is essentially a spark ignition engine, but in many cases in our country, when diesel engines got banned, many people tried to convert a diesel engine into a spark ignition engine. The last thing I will speak about this is that the idea that it can explode by itself is now being researched, and we say, well, what we will do is we will compress it to a higher level so that it explodes by itself and continues by itself. So I don't know spark plug. But such engines are not yet anywhere in the market. They are in the research laboratories. There is no practical way of exactly controlling when it will explode. That is one of the challenges. Research is going on. We do not know if and when it will come in the market. The important thing to remember is that a vast majority of the horsepower that you get is from diesel engines. Petrol engines are very largely used for 2- and 4-wheelers, and in some cases for some types of, say, boat propels, boat engines, and some generators. The capacities are relatively modest. 200, 300, 400 horsepower is about the upper limit to which one starts getting diesel engines. Diesels, they generally do not go to very small sizes, but on the upper side, the biggest diesel engines are like 1 lakh horsepower. And these are used largely in marine propulsion. Almost all your generator sets, except the very small ones, they are called diesel generators because they are diesel engine coupled to an electric generator. And wherever in your city you see a exhaust pipe coming out, be certain that it starts off in a box which has got a diesel engine working inside it. Because of cell phones. Every cell phone tower, if it doesn't get reliable electricity supply, has its own diesel generator. It runs it, provides electricity for the electronics, and also electricity for keeping it cool, which is to run an air conditioner. And across the country, there are more than 1 lakh cell phone towers using diesel engines. So you can think that cell phone, which was not such a great thing as far as environmental effect was concerned, has had a huge impact on the diesel consumption in our country.